So my name is Kobra Khosravian. I'm working in the German Weather Service, and today I will present our latest results of including a new variable, which is called the ZDR column, which is a radar product into our assimilation system. So first of all, what is ZDR? ZDR, or as we called it, differential reflectivity, is a radar parameter that measures the difference in reflectivity between horizontally and vertically polarized radar beam. And it mainly depends on the particle shapes and size and orientation. The higher value and the positive high value of the ZDR indicate that we have usually horizontally oriented particles, which would be like large droplet, rain droplet. And when we have a small ZDR value, it suggests that we have more spherical particle like the hail, small hail, or the cloud droplet. And now what is ZDR column? So ZDR column is a column inside a thunderstorm where the ZDR can be very high. In a real observation, we could see a ZDR value. I should have told that the ZDR values could be between 0 or also the negative ZDR. We also have the negative ZDR, but the positive ZDR is usually between 0 and 4 or 5. And so in the real observation in the ZDR column inside the thunderstorm, we could see a ZDR greater than 2 or 3, and which indicate that we have a very large rain droplet. And then important things about the ZDR column as it should extend above the freezing level. And when you have the ZDR value greater than 2, for example, above the freezing level, it's a sign of having a very large supercooled rain droplet. And also the ZDR column, it's a signal of earlier stage of the hail growth or a very heavy thunderstorm. So it's very important for forecaster if they know that where is your ZDR column, so because they could have a warning in a good time, and it will be used for the nowcasting or a short forecast. How we want to assimilate the ZDR column? The plan to use the ZDR column is to use a method that's already successfully tested and implemented in the German Weather Service, which is the object-based assimilation used for the reflectivity object, so the object based on the reflectivity. And I don't go into the detail, but yeah, for more information in detail, you can see the presentation, the nice presentation from Lisa Neff on 16 June at the ISDA online. And now a little bit about the system that we are using, because we don't use the real observation. So we don't go directly to the real observation because of several issues that the real observation have. And instead we're using the systems called observational system simulation experiment. And it's actually, the difference is that in this system, we're using the syntactic observation. Why we don't use the real observation? The main reason is that main reason is that the poor quality of the polarimetric radar parameter at the current German radar network, particularly compared to the reflectivity. And then another very important one is that we still have pretty large discrepancy between the simulated ZDR from our forward model and the real observation. That is something that we currently work on it. So some of my colleagues, for example, and then we are hoping that we could decrease this discrepancy, but it's still very large. And then above all of that, and using the OC system means that we have a perfect model. And so we have the high control over different setting and parameterization. And so it allows us to use as we want. So use the different settings and parameterization and see the effect of see how our algorithm or assimilation algorithm works. And so just quickly, I wanted to show that how an OC system looks like. So the very important things in the OC system is the nature run. The nature run, actually, it's exactly like the free forecast without assimilation. It's the run that can make for us the syntactic observation. So the nature run gives the input data, the boundary data as the input data, and the initial data, and then it runs for some times, and we use the output of the nature run. We apply a script over it to make the simulated reflectivity or the radar parameters, other radar parameters look like the observation, and then we could give this syntactic observation to our assimilation run. And so the assimilation run, the same as the nature run, gives the boundary data, which usually use the same boundary data for the with the nature run, and then uses also the initial data that can be, in this case, different. And at the end, from the output of the assimilation, we could compare the assimilation data with the syntactic observation to see the effect of our assimilation system on our results. And so now the case study for now that we are using to test our system, it's from 20th of May 2020, which we had tornado. So somewhere here we had a tornado in Paderborn, Germany. So as you can see, besides the tornado, this is a case that we had. So this is the. So first of all, I should have told that this is the real observation, real reflectivity observation from the radar network, German radar network, and this is the PPI scan that's close to the surface. And so you see that above this tornado, we also have lots of places that have a very high reflectivity, and it could have a potential to have several ZDR columns in this area in this time. And so for this time, we run our nature run. I should have mentioned that since it's a nature run, and as I told, the nature run is a free forecast without assimilation. The forecast can be very soon or very quickly far from the real observation. So we don't expect to have for example, something like tornado in the same place, same time. But we know that, okay, in this time we have a potential to have a heavy thunderstorm. And so in this area, in this time frame, we could find probably some ZDR column also in our nature run. And so the nature run, it's in the nature run, we are using the ICON D2, which has a 2 kilometer resolution and with 2 moment microphysics. Our microphysics included 5 hydrometeor, the rain, snow, graupel, hail, and then ice cloud. And the initial data came from also a 2-moment experiment. It's called ICON Book. It's one of the operational icon in the here in Deventer. And the boundary condition provided from another operational icon called ICON EU, which is 1 moment and over the European country. It's a bigger domain. And so here it's our output, the reflectivity and then ZDR. Actually, we usually have the radar. We usually have the radar product output of the radar grid point, exactly as I showed for the real observation. We usually make our output over the radar network and the radar grid point. But here we thought that okay, it would be much more easier if we would have the reflectivity and the ZDR over the model grid point and our model domain, since can use it easily into our assimilation system. So here is the DPZ, the reflectivity and the ZDR, which was qualified, which was done the quality control. And then after that, you see that DBC and then ZDR. And the place that was more interesting, or the region that was more interesting for me, was somewhere here that I thought that I could find probably some ZDR columns here. And I would just zoom in this area. Okay. And then applying my algorithm. I mean, of course, the algorithm is applied over whole domain, but I just zoom in this area to to see better, find that grid point. And how the algorithm works, actually we tested different methods, but the one that was up to now, it seems that it's the best one and it has the more appropriate results for us, is that the algorithm finds In the first step, find the zero level temperature, and then it search for over all grid points, and then find the grid points that have the reflectivity greater than 25, 500 meter below the zero level, and 500 meter above the zero level. And also the ZDR, which is more important, should be greater than 0.5 dB below 500 meter below and above the zero level. These numbers are not really consistent with the paper you can find about the ZDR column. So usually the threshold of ZDR is 1 or 2, or you have to go like 1 kilometer above the melting layer to be sure that it's a ZDR column. But it's actually based on our ICOM model, because we thought that, okay, I mean, as I talked with our modeler, we thought that, okay, the threshold that are in the paper cannot be used for our ICOM model. And if I use this threshold in the paper, I found almost nothing. And I will go that why we have some, I will go into some details that why we have some problem like this. But yeah, I wanted to say that it's not really consistent with the paper. And so based on this algorithm, the algorithm find for me like 12 points that are somewhere here. And then I looked more into the grid points that was found by the algorithm to see if there are really some ZDR column or not. And here you see the reflectivity and the ZDR profile of these points. And you see that, for example, for reflectivity, we have a very high reflectivity, about 60 dBz. But the ZDR, as I said, on the surface is 3 dB, which is very high, but then it goes to the upper level, and particularly when they're going above the melting layer, the ZDR decreasing sharply and goes to 0. And so, as I said, I cannot use a threshold of 1. And another variable which is also important, it's a vertical wind. That's, you see that here it's about 8 meters per second, which is a very high vertical wind, and it shows that it could be a real ZDR column. Some other important variable for us is look into the hydrometeor variables, and here I show the mean diameter of the rain droplets on the surface and above the melting layer or the supercool. As you see, the diameter of the rain droplet on the surface is about 1 millimeter. And then when I go above the 0 level, the droplet of the rain, it's about 400 micron, which is pretty small for this case when we have the ZDR column. We expected, or in reality, we know that the droplet in this case should be much bigger. And for example, if I look into the hail, you see that we have a hail bigger than 1 centimeter on the ground, and also we have a hail bigger than 1 centimeter above the melting layer, which is pretty large hail. But yeah, compared to the hail, we have very small rain droplet. So we thought that, okay, before going to assimilate the ZDR, we can probably do some modification in our model microphysics to improve the diameter of the supercooled water droplet, or to at least to see the effects of changing different parameterization. Here, the two change that was important, and then the main change that we, I will show you the effect of these two changes that we did in our microphysics. The first one was increasing the size of the aerosol's nuclei, which is the nuclei of the rain droplet, by a factor of 5 to make the rain droplet bigger. And then there is also a procedure that calls breakup process in raindrop growth, and we turn it off to make the rain. So it's a process that in some part it says that the rain drops should not increase the same speed of the very small rains. And so we just turn it off to make the raindrops even bigger. And then we run our algorithms, run our models and our algorithm again. And so again, if I zoom in this area as before. Okay, so now when I applied my algorithm, the algorithm find like 5. So first of all, the algorithm find the ZDR column somewhere else also, but it finds just 5 ZDR column for me. So it seems that probably we make some bigger droplets, but it falls down faster. And then again, I wanted to look into my ZDR column, and then you see that again, I have a very nice reflectivity, bigger than 60 on the ground, and then about 60 above the melting layer. And then ZDR also the same as before. I have like 3 dB ZDR on the ground, and then but then when the ZDR goes above the freezing level, it's decreasing sharply, and it goes smaller than 1. So it's still I cannot use the threshold of 1, for example, for the DBZ. The vertical wind, it's even higher than before. Now I have the vertical wind about 40 meters per second, which is a very, very high vertical wind. And so now let's look at the rain droplet diameter. So as before, I have the, I have like 2 minutes. Okay. I have the diameter of 1 millimeter on the ground, and then when I go to above the freezing level, you see that I have some improvement in the diameter of my raindrop, which is 800 meters. It's kind of doubled now. And for the hail, you see that I have a bit bigger hail on the ground, but above the melting layer, now the hail become smaller, which is some good news. And so by this, I will go to the summary and outlook. As I showed, the first step for us was to making our OC system, which was successfully tested and implemented for the radar reflectivity, which I didn't show, but the OC works well for the reflectivity, and it was for us a good news that, okay, now we can use the OC for the ZDR color. And then we had the ZDR output over the model grid point, and we did quality control, and then we've been sure that it was for us next step that this ZDR output over the model grid can be used now for detecting the ZDR color. And as I showed, the icon model with the 2-moment microphysics showed that it can produce the ZDR greater than 0, but above the melting layer. But as I showed, still it's not really big enough, probably. And the main problem is that we have a very small supercooled water droplet, and we will do further investigation and analysis into the size of our water droplet to be sure that we could get better results, for example, or to see that which parameter can have a better impact of the size of the water droplet or rain droplet. And then after that, the next step would be to define the ZDR column as a new observation object, the same as the reflectivity object, into our assimilation system. So yeah, thank you for your attention, and I would be happy if there's any question to answer that.
Okay, great. Thank you, Kobra. Very nice talk. We do have one question, and we have time. So Philip asks, do observations of ZDR also have this very strong peak close to the surface?
Yeah, because close to the surface we have, I mean, the ZDR, as I said, when the ZDR is very high, it shows that you have a very large rain droplet. So it seems that we have the very large rain droplet close to the surface, but when it goes upper, the rain droplet either freezing, or in this case, for example, when we are near to the melting layer, either freezing or they drop off very fast when they become faster, and so we could not have the rain droplet a bit above the surface. But yeah, near the surface we have a very high ZDR because probably we have a very large rain droplet.
Okay, great. Thank you very much.
Yeah.
Okay, thank you.